So I did forget to just introduce myself earlier on. So for those who don't know, my name is Rick Van Dam. I'm an independent consultant these days, but prior to that, involved in sort of government research and monitoring for 20 odd years in water quality and ecotoxicology, and along with the likes of sort of people like Chris Humphrey and Graham Batley Ross, been involved in the water quality guidelines space sort of since the mid to late 90s. Okay, so as I said, I'll just provide a little bit of an initial overview around determining water sediment quality guideline values and associated water quality objectives. Very briefly touch on guideline values or limits, if you like, for pressures. Most of the content of this topic is around guideline values, water quality objectives for stresses, and Chris will focus on physical and chemical stresses, and we've got case studies, and several of us will talk about toxicants, and we've got some case studies, and then back to Chris and a few others. Yeah, so physical and chemical, it might come later, but yeah, so physical and chemical stresses, we're effectively talking about those natural stresses like pH, water quality, variables pH, salinity, conductivity, nutrients, dissolved oxygen, suspended sediment, that can have an impact on ecosystems in various ways. Toxicants is self-explanatory. We're talking about direct toxic effects of contaminants, both natural and anthropogenic, so metals, organics, etc. Is that good, Chris? Thank you. Okay. And hopefully, I think I've been sitting next to Ross for too long and my voice is heading in the same direction. So guideline values for pressures, it's an unusual term, probably not used that often. And Chris has gone through this morning around pressure indicators, stressor indicators, ecosystem receptor indicators. So again, that PSER approach, as he said, flows through the whole process. So the pressure indicators are more often used as supporting or explanatory variables. And as Chris flagged again this morning, that it's often important to include those that are unrelated to water quality to help better attribute cause, etc., to work out exactly what it is causing the problem. But guideline values, or they're often referred to as limits or thresholds for pressures, can be set. And I think Clive talked about that in terms of EPA licensing discharges. So they license the discharge and they're not looking at anything in regards to stressor guideline values in the receiving environment. So we're looking at things like load limits or alternatively end of pipe concentration limits. You can even use just effluent toxicity per se as some sort of threshold or limit. Just the example up there is one from Sydney Water and one of their wastewater treatment plants, and just sort of showing again that from a licensing perspective, the wastewater industry typically has pressure limits applied with regards to nutrient load limits and other load limits around other stresses as well. So the thing about pressure indicators is they can be of use when you're dealing with these highly variable, unpredictable receiving environments where it might be very difficult to monitor and set relevant and appropriate thresholds for the receiving environment. There's still levers you can pull with regards to setting limits or guideline values for pressures to help manage water sediment quality. Okay, that's all I'll say there, and just move on to stresses. This is like the big important flag, basically, just to flag, and this goes to the whole idea that we need to be less reliant on solely on the numbers and thinking a little more holistically when we're doing our water sediment quality assessment. So the stressor guideline values are just estimates, and depending on how they're derived, some will be better than others, and you'll get a feel for that as we move through. But they really just get you in the ballpark of where there might be a risk, and things might start to be unacceptable. But by and large, they shouldn't be used alone as the sole line of evidence, and that's where the multiple lines of evidence approach comes in. Okay, but we still end up devoting a lot of time to guideline values and how to derive them, etc. Now, so in the water quality guidelines, there's a strong preference for you to derive your own guideline values. So that's local or site-specific guideline values, because they'll be most relevant to your system of interest. They'll take account of, if possible, the types of species that occur, the types of water quality that occurs in your system. So the way the guidelines are structured is that that's the preferred approach. That's the first approach. If you're unable to derive local guideline values or you're waiting on them, then there's the option to choose default guideline values. That's how it should work. And in reality, you know, people still tend to go and pluck a number out of the default guideline values, but obviously it's a cost-effective approach. So there's a lot of obviously information and guidance around default guideline values in the website too, and hyperlinks are there for people to go to and have a look. Again, this is all rather generic and general. It's not specific to temporary waters. Cool. Okay, so obviously the preferred approach is for deriving guideline values. So the guidelines provides guidance, quite a bit of guidance on how to derive guideline values. And they can be derived based on different types of data. And we will go through these. So this is just an overview. So basically we're talking about the option of deriving guideline values using reference site data, using laboratory effects data, moving through to field or even semi-field effects data. And then there are approaches where one can rely on more than one of these to derive guideline values based on a multiple lines of evidence approach. Typically, but not always, tend to go from less preferred up here to more preferred down here, but that will depend on the situation. There may be some instances, for example, perhaps high conservation ecological value systems whereby you want to effectively be focusing on reference site data and looking at no change from background, etc., because of the high conservation value. So that can flip around a bit. And these approaches, because they're based on types of data, they're generally applicable to both phys-chem stressors and toxicants. Okay, so just before we head off to Chris to talk in more detail about phys-chem stressors, so just some of the issues that are relevant to deriving guideline values for stressors in temporary waters, and this is a selection, it's not exhaustive. One of the things that's been flagged already, and it seems to be one of the bigger issues when we get to talking about temporary waters, is that the exposures can be transient, so they're pulses, they come and go, they're unpredictable, they're variable, and you've got that common problem that the default guideline values may not be applicable. Hence, of course, it's preferred that you derive site-specific, but that can be challenging for temporary water environments. How do you do that? Lack of reference site data due to ephemerality. So it takes a long time to build up a data set. So one, it can be hard to find a good reference site. And two, it takes time to build up the baseline because there's not always water present. There are ways to sort of get around that by replacing your temporal replication with spatial replication, and the guidance document talks a little bit about that. We've got the challenges of locating suitable reference sites. Again, as people mention, it's difficult. You've got the, I suppose, the issue of best available reference sites and what's involved with that. I think it's already been flagged as well, but rapidly changing water quality as these pulses move through, and even in sort of long-term remnant or refugial pools as they evaporate, etc. As certain things happen, processes happen through periods of time, that water quality changes. So what's considered representative water quality here, and how does that affect things like contaminant bioavailability and toxicity? So how do you come up with a relevant guideline value for a very dynamic system? And then a bit related to that, consideration of physical and chemical extremes. And again, how does that impact what's a relevant guideline value? The issue of key refugia versus ephemeral reaches, which ones we need guideline values for both? Will they be the same? Possibly not. And they might even have different levels of protection assigned to them as well. And then seasonal sensitivities associated with different phases of the wetting drying cycle. I think Chris talks to that a bit. And as WA flagged, paucity of data for local species are the data that underlie guideline values, or the species that underlie the guideline values representative of some of these unique and different species that occur in temporary water systems. So just some of the things that have to be considered, and hopefully we address a few of these as we go through. Okay, I'll hand over to Chris if we've got time.
I'm not sure if I'm preempting this too early, but one of the major things that's come up in this conference is the issue of multiple stressors. And I'm just wondering, like, has that been considered at all, a standardized approach as to how multiple stressors like increasing temperature are going to be, how are people going to be able to work out a guideline value for a site when there are these multiple stresses present, like increasing temperature or increasing salinity along with contaminants? Yeah.
There's not a lot of, well, there's not, Chris or someone can correct me if I'm wrong, if I'm forgetting something. There's not a lot of formal guidance in the guidelines at the moment about how to go about that. As you know, the department is going through the strategic planning process, and multiple stresses has kind of been on the list of things to tackle soon for a while. So I think it's an opportunity to maybe, you know, some of the priorities might head in that sort of direction. Again, if you've got the ability to derive site-specific guideline values and you know your system well, so your conceptual model's good and you understand what some of those multiple pressures are, you've got the ability to do the research to derive guideline values that take those things into account. So, you know, if you've got certain co-stresses, temperature, salinity, or whatever, associated with certain contaminants, you know, one can design experiments and research to actually generate the data to derive values and so forth. It's not a cheap and quick exercise, but it can be done if you understand the system and what those key co-stresses are. But yeah, it would be good to see more guidance, in short. I don't know if Ross or
I mean, direct toxicity assessment, of course, is one component.
Yeah, but I think that reality certainly underpins a lot of the emphasis put on conceptual modelling of pressure, stresses and ecosystem receptors, that whole framework, in order to try to capture some of that. And also the push towards weight of evidence assessment approaches, because you need better inference when you've got to tease apart the effects of multiple stresses on a system. And at the end of the day, you'll probably have management options for 1, 2 or 3 of them, but you won't have management options for all of them. And you need to be able to distinguish what's causing the most concern and what needs to be the priorities for management. So yeah, absolutely.
We've actually got 5 minutes before lunch. You're a bit longer than that.
Yeah, okay, we can start up.
Yeah, let's break it 5 minutes early. Yeah, sorry, are there any more questions? We've got 5 minutes, so.
Rick, this would be a very technical question. When we derive guideline values using reference site data, these temporary waters, that water regimes getting changing, that the people who the industry is collecting reference site and impact site data, they always collecting once a month or something like that. And when they use this data for guideline value deriving, how they pool these things, because they are sometimes in these riverbeds, as I know, there are some pools. They are collecting water from there as well. And there are some data could be like changing from flowing water to the pool water. It is very like very technical things. But I would like to know the people in here, how they can address these things.
Yeah, I think that'd be a good idea. I think it'd be a good idea to touch on that after at least my presentation, where I deal with seasonal and spatial variability, at least with the physical and chemical stresses, and maybe that we'll go from there.
Want to say anything? Okay, if there's no more questions, there's none coming through online that I can see. So we'll break for lunch. We'll be back in 45 minutes. So what is it? 12? All right, we're going to get going. So we're starting with Chris. We've got everyone we need, Chris? Do I need to? We've got Angel. Okay, fantastic. Take it away. We're going to do physical and chemical stresses. Thank you.
I think Rick mentioned earlier that the stresses can be derived in one of two ways. That's biological effects based or using reference-based information. And for physical and chemical stresses, while it's preferred to have a biological effects-based approach, the most commonly applied method is simply to look at a reference-based approach. So what we're going to look at here is accounting for seasonal and hydrological variation inherent in these temporary waters. We'll look at sort of two scales, basically deriving guidelines within the catchment or water body. Then we've got two case studies for deriving regional guideline values. One using a reference-based approach based on the Indian Ocean Drainage Division that was prepared by hydrobiology, and then a biological effects-based approach that was done from South Australia. But before I go there, I'll just give a little bit of history on derivation approaches that are sort of, I guess, the evolution of the water quality guidelines since the 2000 revision and where we might be heading to now. So this was the basis of the 2000 guidelines that in terms of the regional guideline values, the states and territories contributed a whole lot of physical and chemical stress data that was gathered over a 2-year period over the different months. And basically the default guideline values in the 2000 document just came up with the 80th percentile of all of that seasonal variation. So that in this case here, you've got high natural turbidity at low summer flows in those blue cells, but it was all of that variation was subsumed within the entire data set. So it didn't give much resolution at all. So that's what we ended up with in terms of the regional guideline values. And as I say, that's led to quite coarse water quality assessments for that reason alone. And there are other reasons for that as well in terms of compiling information from across an entire state. But that's another matter. But what did happen in the 2000 guidelines was that for, I guess, a more site-specific approach or do-it-yourself approach, there was a recommendation that you have a rolling 2-year median and 80th percentile, so that at least you incorporated some of that variation. But notwithstanding it, there's a lot of places around that just used a sort of a static reference data set that was collected over a baseline period and didn't factor in interannual variation. And then we've used that particular basis for looking at exceedances outside your 80th percentile. And even at Ranger, we've still got relics of that very basic approach in some of the parameters. But yeah, this is an advancement, and it looks at your rolling 2-year medians and looking at the 50th percentile over the 80th percentile of the previous 2 years. So where the current revision 2018 and the guidance document also picked up on is, so I'll go back one. Oops. Okay. I better go through the whole animation. There's a, once you start to compile a bit of information, you can see patterns in whether it's discharge or season. And this left-hand one most is a wet, dry tropical river where there's distinct patterns in turbidity and electrical conductivity associated with discharge. The next one over is from Magilla Creek. So this is data that have been gathered by Energy Resources of Australia over the last couple of years, exemplifying the pattern of nutrients in these small streams that with first flows, early flows, there's a lot of runoff of organic matter and nutrients into the system. That gets depleted over the wet season with flushing, and then it kicks up again at the end of the wet season from 2 reasons: from evapoconcentration, but also you've built up quite a primary production base in the creek itself, and that's starting to senesce and to contribute nutrients. Then I picked up this one here, which might interest the Lake Eyre Basin people, which was the publication from Sheldon and Bellows. And it interests me because I think the paper seems to paint a negative picture about variability, but if anything, what I saw was, and what I was getting at in one of the earlier talks, was distinct multivariate pattern. So, and predictable pattern too, in that in a flow period, you're more likely to have homogeneity in your variables. And as your system starts to dry out, then you get in the influence of, stochastic events that are occurring in just the individual pools. So that by the no flow period, there's quite a bit of variability. So we just take that. I'll take another example, and in terms of what's been done in the current 2018 guidelines. And this is something that interested Brent Henderson from CSIRO, and he's a good one to engage on this sort of stuff and how to deal with variability. But basically, yes, we can partition the data into seasonal or hydrological components and look at the covariance of that variation. In this case, we've got discharge against electrical conductivity. Okay, sorry. So, yes, we can partition the data by season, or we can actually fit regressions to the continuous data. In this case, we've got continuous monitoring of electrical conductivity as an indicator of salinity. And what Brent did was simply to fit, through quantile regression, just fit the 50th and 80th quantiles, which match up with the approach that's been recommended since the 2000 revision. That is, when you're monitoring for exceedances, it's the exceedance of a new population outside that 80th quantile. And this is rather unremarkable, but in terms of, something like the Lake Eyre Basin, similarly, you've got a multivariate pattern there, and for those 3 seasonal groups, you can pull out the individual stresses that contribute to that and derive your 80 percentiles. But, maybe more radically, you're looking at something that's simply looking at the physical and chemical status of the system. So whether or not that whole status of that water quality cloud has moved outside of that, what might be termed as sort of a baseline or reference condition. That's all I had to say, but I think Angela's mentioned earlier that she had other ideas on this, or whether it's related to stresses or biological indicators. I'm not sure.
Thanks, Chris, very much. I did have a quick look before I came to this event at the Sheldon and Fellows paper. Unfortunately, I couldn't get the whole paper online, but I'm aware of it and I know what she's saying. Well, she's saying too, she's really saying that there are differences between low flow periods and high flow periods, and we should set criteria for those two at least, or maybe more, maybe some intervening period. So I've been talking to Kate Bernard about that sort of idea. But we do have matching biological data
Yes.
from Cooper Creek.
Yeah.
And in my very first paper, I wrote about the beginning and the end of a dry season. We've got turnover data on how the water quality changes, how habitat changes, and how the fish communities change and which species statistically respond to which physical and other factors.
Well, that might be more akin to the South Australian presentation because they do have a biological effects-based approach for the physical and chemical stresses. So we could probably catch up after all of that. That's it. Who's next?
I flick to the next slide. We'll work it out.
Well, yeah, of course.
And you just tell us when to flick slides and we can do that.
I can probably go to the next slide. And I can, yeah. So, yeah, thanks for the opportunity to talk. We're really talking about a program of works that happened a few years ago now, I think probably 2017, that the Ecoregional guidelines were revamped and updated. And we did 3 different regions, basically to try and replace the Northern Australian single guideline value, ecoregional guideline value. I'll show you a map of where we've done the studies shortly. But it's really about essentially updating the ANZAC ARMCAN's guidelines that were 17 years old by that stage and a bit older now. We wanted to develop water quality and aquatic health indicators based on basically more data and more sort of regional data rather than just lumping the whole of Northern Australia together. We had progressed, I guess, since the last guidelines were released, and there were things like continuous monitoring. There were more parameters, there were more sensitive analysis of those parameters, and remote sensing had improved. So we thought it was time to improve our guideline development as well. And the existing ecoregional guidelines for physical and chemical stresses provided deficient ranges, particularly when you looked at regional systems, and particularly in relation to widespread catchment scale pressures such as grazing and agriculture. And there was a decision to move from regional guideline values based on state boundaries to guideline values based on physiographically similar water types. And that was across Australia's 13 drainage divisions, but only 3 of them were actually updated as part of this process. Okay, we can go to the next slide. That'd be great. It's going to focus on the Indian Ocean drainage division, just to get plug a bit of Western Australian input in there. But it was also done for the Timor Sea and the Gulf of Carpentaria. The Gulf of Carpentaria and the Northern Territory part of the Timor Sea Drainage Division was greatly helped by data provided by Queensland and the Northern Territory. So I just have to plug that. And in Western Australia, by the state, the regulator here and the state databases that they had. So we gathered and processed all of the water quality data that was provided, compiled by the supervising scientists. That was for the NT water quality. We then combined that in a GIS system, and we did a lot of data vetting, and we tried to classify it according to the Australian National Aquatic Ecosystem, the ANAE classification framework, which is worth looking into if you haven't seen that. There's a great document that describes how to classify aquatic ecosystems on a national scale. Ecosystems. Yeah, and then we then we developed the statistical ranges, the medians, the 20th and 80th percentiles for those water quality parameters. So we can go to the next slide, that'd be great. So the parameters that we focused on were mostly physicochemical. We did a little bit of sort of major ion analysis as well, just because we had the data and we thought it was worth processing at the same time. But it was really about looking at what parameters we actually had rather than all the most desirable. We would have loved to have had things like dissolved oxygen and even more data in relation to some of the nutrients, but there just wasn't enough data in the database. The N values were too low. So major ions are not part of the guideline values for stressors, but we did some analysis on those just to explore the relationships between major ions and catchment scale patterns. So there was some less than reporting limit imputation. So there's various methods statistically you can do that, where you essentially replace less than detection limit values with imputed or estimated values in order to make the guideline or the statistical ranges more accurate, I guess. So there was data divisions reported for each 10th percentile, which means, you know, over the bell curve, we reported values for each 10th percentile. And where there was insufficient data of less than 10 values, we didn't put anything in there. And then we had two other categories. One was low reliability or indicative guideline values. And the other one was moderate to high, which related to a sort of 10 to 20 values or greater than 20 values respectively. So, and that's acknowledging that 20 values is not a huge amount of data to characterize an entire water quality sort of range for, you know, an entire region, but that's where the data set sat. We can go to the next slide, that'd be great. So this is a little bit about the principal component analysis that was done, looking at the ecosystem characterization, the ANAE level 3 groupings, which were lacustrine, so lake systems or riverine lake systems, riverine systems, and palustrine, which is really sort of wetlands, vegetation dominated aquatic systems. We also looked at climate zones. So I think it was Chris showed a slide of Kennard et al. So we used the Kennard's climate zones and also the water quality data set. We threw all of that into a principal component analysis, and we found that there was some grouping around the different habitat types, the palustrine, riverine, and lacustrine. We also added salinity in there in acknowledgement that it's an ecotox-based parameter. It's also very important within those groups because you can obviously have systems that are ranging from very fresh down to hypersaline over the seasonal range of values. And you can just have systems that are naturally saline and systems that are naturally fresh, even though they sit within the same sort of ecosystem. So lacustrine, for instance, salt lakes versus freshwater lakes. You can see on the right there is just a table of the N values, the number of data sets we had. And you can see that for fresh riverine sample, that's for desert and grassland, and for subtropical climate zones, we only had 6 freshwater data. So that's within the Indian Ocean division. Yeah, so once you broke each part of the data set up into habitat types and climate zones, it really did reduce the amount of data available for any one bin or any one guideline value. Okay, we can go to the next slide, that'd be great. It's just a quick map of where the various habitat types were. You can see the vast majority of them were riverine. Not a lot of lakes in the Pilbara, and has been alluded to before that where there are lakes, there's salt lakes and nobody monitors them because people don't care about salt lakes. So really the vast majority of the data is to do with freshwater flowing, mostly temporary systems in the Pilbara, and probably mostly around permanent pools where the focus for monitoring. So palestrine wetlands, the vegetation types, the vegetation dominant wetlands were separated from lacustrine riverine systems. They were largely driven by turbidity, and some were also influenced by pH and conductivity. And climate zone analysis clearly separated subtropical environments from desert and grassland systems. So that's really why we chose those divisions, because that's what the stats showed us, that there were divisions there to be found. And then the wet and dry season was also separated out, based on the principal component analysis. And they're pretty crude, wet and dry season. We had to, in the end, go by month, which isn't ideal. It's just that having to go back over 30 years of data to work out whether a particular sample was taken during a wet period or a dry period was an almost impossible task. So we just went with by month, whether it was a wet or a dry season. But obviously, some of the wet season months might have actually been at the end of the dry season and vice versa. Go to the next slide. That'd be great. Just briefly, you can't really, or we can't see much. I don't know whether you can see it on your screen, that the actual numbers, these haven't been released, so it's really just for discussion purposes only. And that really just shows a table of the sort of numbers that were generated. And what you've got there is you've got the ecosystem type, or the hydrology type, really, the palestrine, lacustrine, or riverine. And then that's broken down into brackish, saline, or fresh systems, which is then further broken down into wet and dry seasons. And there's ranges and percentiles for each, like a median and 80th percentile and a 20th percentile. I'm not sure if you can see on that graph, but there is an N value there for each, like how many actual samples we had to derive that range. And a bunch of them have got insufficient data next to them. I think that might be it. Is that the end of the slide deck? Yeah. So if anyone's got any questions on that, that'd be great.
The lady for the microphone. Thank you, Phil. We can see it clearly here, lots of numbers. We can clearly see lots of numbers. Look, and I apologize to those online. We'll work something out for you guys if you're really keen on some of this content. The slide deck will go around to people for a start, so you'll be able to look if it's too fuzzy to see on your online Zoom meeting. Anyway, questions? Here's Chris.
This is more an observation and one for Tony and his team and the water quality team, but I understand that these no one's actually applying these guidelines in Western Australia, and they're using inappropriate guidelines, Ross, and they're not available yet. So it's a question of resourcing within the water quality team, and getting these available to people as soon as possible, because it's They're now how many years old? Just, come up to about 4 years ago, 4 years old. Yeah. Just a comment.
I'd like to add to that too, that I think one of the outcomes was that we know there is a lot more data out there, and we would really, I think there was some reluctance to issue the numbers, knowing that we could probably fairly simply improve them if we could just get hold of the new data sets and then find the resourcing to actually process them and add them to the previous work that's been done. So so I guess that's another issue, is whether or not we can get a lot of the privately held data sets, because in Western Australia, at least, as with sounds like South Australia, the amount of public water quality monitoring has drastically reduced in the last sort of 10, 15 years. So really most of the data sets now held in private hands in mining companies and the like.
Yes. Ross.
So yeah, just to add to that, I've been involved in court cases where people have been prosecuted on the basis of whether they were above or below the default guideline value for pH in Northern Australia. And I don't know what the N value for that is, but I absolutely have no faith in that number. Yeah, I know. So I really think we need to get these numbers available, and I actually think it's a strength that we overtly say the N numbers that they're based on, because it would really welcome people to improve them for their area and get more data and make it more available and improve these numbers. But if we don't start somewhere, how we'll do it, and the fact that courts are relying on those old numbers, which are just meaningless, is worrying.
Yeah. Chris, I'm coming over. We've got a question from Chris Williams, Dropwater.
I don't know the regulatory compliance regime in WA, but I'll observe that in Queensland, and I know this doesn't apply to Queensland, but in Queensland, even if new numbers were issued now, we couldn't use them, because we're using a structure of the environmental authorities, which takes a very long time to change, costs a lot of money to change. And even when, we can use new data, new numbers in investigations. We can use that for assessment of probable harm when we're allowed to assess probable harm, but compliance is based on a fixed number in a fixed legal document that doesn't change with the science. So that's certainly an issue for us here.
Thanks for those comments. Anyone else? Sorry, I've run away from my iPad again. I probably could have used a bit of help, but I'll double check. Oh, actually, I could probably see it on the screen. There is that a question? Yeah, okay. We've got one. Quality has now improved significantly for me. Oh, many thanks. Just a comment on it. I'm glad it's working. Not a question though. Okay. So thank you, Phil. We really appreciate your efforts. It's great work, and it's great to see it up on a big screen. And yeah, we'll move on to the next presentation, which is back in the room with Clive, I believe. I think so. It said South Australia. You are South Australia today, mate. This is on behalf of Peter Goonan that couldn't be here. And we really appreciate you stepping up, mate.
Pretty dodgy. Pretty dodgy. Not the thermodynamics.
Right. So South Australian guideline values. We've accessed 20 odd years of monitoring data in South Australia and plugged it into the Titan software. I didn't know what Titan was until last week, so we'll see how we go here. So change point analysis, got a couple of funky graphs to show you, and I'm sure other people down here can interpret it better than me. But I gather it identifies along a stressor concentration gradient, a point at which sensitive species become less abundant, and when more tolerant species become more abundant. I don't know how that's evaluated statistically, but yeah, you've got these Z- and Z+ scores. Good. So we've done that for a bunch of regions in South Australia, or bioregions that are not just catchment based, but we've divided the state up into what are sensible regions. For macroinvertebrates, or animals, but basically macroinvertebrates, the diatoms data is, I gather, statewide, one sort of group. Yeah, so let's just see what the graphs look like. Really, yeah. Clever people down here might be able to tell me what this means, but I gather like the red trace is the sensitive species, and as you got on the x-axis, an increasing, that's in the case of nitrogen as a stressor concentration. You've got obviously a decrease in the abundance of sensitive species, and the blue trace is an increase in the abundance of more tolerant species. That's the extent of my knowledge, and there's this other graph here that does something slightly different. Anybody else can say something intelligent about that, please go ahead. But that's using data that we've collected over a large period of time. Now, I think there's, oh yeah, so, and there's some of the regions where we've come up with guideline numbers that fall out of that process. When it says the far north, that's everything in South Australia, pretty much above Port Augusta, which is a massive chunk of land, versus Kangaroo Island, which is much smaller, etc. So now, please be aware that prior to this, the guideline numbers for phys-chem stresses in South Australia were based on the work done by a water quality chemist in the 1990s who collected data from locations that were supposed to be referenced or minimally impacted. They were actually, in hindsight, pretty badly impacted. So they were really not representative of anything like reference conditions. So if we pick on nitrogen on the right-hand end of that table, across the state, the current guideline number for total nitrogen is 1 milligram per litre. So this Titan analysis suggests that that's going to change quite dramatically. We can't use these new numbers at all at the moment because our legislative framework is still hooked into the 2000 version of guidelines, which are data from that historical, poorly representative set of locations. But we're ready to go when we change our policy in the next couple of years, and it will come. So we've worked with University of Adelaide, John Tibby. Apparently he's a really clever biologist, and so we worked with them on the Titan analysis. We've also got this arrangement, which is an outdoor purpose-built biological effects set up for guidelines derivation. And Peter Gurnham is trialling this at the moment with suspended sediment or turbidity to try to come up with, or this could be used for the other phys-chem stresses as a way to validate the Titan analysis. But conceivably do it for other parameters where the Titan analysis isn't useful. So this is a flow-through mesocosm setup that was the design was borrowed from work done in Europe, I gather. But yeah, over a period of time, carefully collected species are subjected to a range of stressor concentrations, and they measure the biological responses. And that's about as far as I know. But anyway, it's I'm not sure that's going to be applicable to all of South Australia because it's based in Adelaide, so it's going to be the Adelaide temperature regime. But yeah, that's, I think, that's been published also in collaboration with the University of Adelaide and John Tibby's group. I think that's the extent of these slides. Yes. So Titan is our world, and we're going to try to validate the Titan software analysis with biological effects assessments. But the biological effects assessments is still in the beginning stages of implementation.
Thanks, Clive. Great job. Great job. I have used Titan. It's been a while since I've played with Titan, but I'm a fan of Titan because it does do those individual change points. So you can actually pick out perhaps the sensitive indicators from it. But it's been a while. When we were doing this, I showed the Titan analysis that we've done for sediment quality guidelines. I did ask the authors of the software, should it be used for environmental regulation? And didn't get a funny response. It's a very long response. I can't remember what it was, but I guess there's a key question about whether the change points that Titan throws up, whether that means the change has already happened and it's sort of not conservative enough, but it seems to put up pretty low numbers. But one of the greatest things I saw at this conference this week was Marie Thomas. We did a little mesocosm study, and they're using those change points in their species sensitivity in a prokaryote sensitivity distribution. So you can really use those numbers in perhaps some novel ways. Chris has got a comment. Right.
My comment is that it is a bit of a black box for most users, and Ross is going to show other ways of doing that. So I just would prefer that if people are going to do that, they look at some other approaches to the data analysis to see that there's some corroboration. But yeah, Ross's approach to deriving, the same sort of approach to me is more intuitive, but just because it's not a black box.
I think black box is a little bit unfair. I think it's Susie, but I really like that you're taking it and testing it. I mean, I think that's the important side of what you do.
I've noticed a bit people are putting up total nitrogen as an indicator, and I've had terrible problems with that because it depends if it's ammonia, oxidized nitrogen, or organic nitrogen. So they're digging deeply into that, more deeply.
We've explored that. Ooh, really. And yeah, the data shows that the total concentration is all that we need to explain variations in biological response. We're apprehensive about speciation of things like nitrogen because of the monitoring complexity. The analytical cost goes up, the field methods get more complicated, and the benefit cost isn't really there for. So we get enough benefit out of the total concentrations. It suits our purposes.
Chris, definitely related to that.
Experience in that area, in that sense that the inorganic forms can be just stripped out of the water column, so they're virtually just detection limits. So we found that very unuseful to be looking at those inorganic forms. In the T and the TP, actually a bit more robust and looking at the entire fractions, organic fractions as well.
Thank you. Any other questions, comments, observations? And I could talk for a long time about Titan, but I reckon it's not fair without Peter in the room. And at some time we'll catch up. Maybe we should do a special statistical threshold modeling thing, because some of these things are really are needed. And we found that when we did that sediment study, that there was very limited tools for doing threshold analysis for field data and things like that. So and we've been talking about it for a long time, and there are ways you can do it, but putting them all up together would be fantastic workshop. Anyone else? This is you, Rick?
Yeah.
So guideline values for toxicants is next. Take away, Rick.
Thanks again, Andrew. So this is me and Shelley and Ross Probably Clive again. Sorry, just joking. Okay, so we're moving on from phys-chem stresses to toxicants. And as the same as Chris talked about with phys-chem stresses, for toxicants, you can derive using either sort of non-effects based approaches or effects based approaches. So the non-effects based approach being the use of reference sites. That can be done in particular for naturally occurring toxicants, metals and metalloids, etc. One thing that one needs to be careful about is regions of high mineralization where you've got naturally high metalloid concentrations that might be approaching the tolerance thresholds of species. Those systems may already be under stress to some degree, and to allow the median 80th percentile approach where you're allowing the median to approach the 80th percentile may potentially be pushing those systems above those thresholds and further stressing them out. So, and you may need to be more conservative in the percentile you choose. So that's just one consideration with regards to using reference-based approach. In terms of effects-based approaches, but using toxicity assessment is one way, whether that's single toxicant or direct toxicity assessment, as Chris alluded to earlier. But of course, as we come back to today, regularly you need to consider a number of factors, primarily exposure scenarios, and we immediately think about pulses, and also the relevance of the species that are being tested and the life stages too. But these are things that can be worked through and considered. If one wants to capture more of the local conditions and the local variability, then we switch to looking at sort of semi-field effects approaches, which we're kind of seeing for phys-chem stresses case studies as well. And Ross will talk on that. We've got a couple of case studies on the pulse exposure side of things as well that we're about to get to. And of course, guideline values for toxicants and sediment as well. And that includes where you can use sediment as a proxy for water quality. Andrew spoke to that earlier, so we won't talk about that now. Refer back to the uranium example that Andrew gave under step 3. Okay, so 3 case studies. The first relates to deriving guideline values and turning them into and implementing water quality objectives for magnesium based on pulse exposure toxicity. So apologies, folks, it's another Ranger example. But for Ranger, continuous monitoring, as you can see on the plot on the right here, shows that you basically get pulses. The discharges primarily occur in pulses. What we've got here is effectively EC downstream mine. The upstream traces just kind of bobble around down here somewhere. Discharges occur in pulses, sort of minutes to hours, and you can start to see that the actual nature of those discharges in that system and start to ask questions about what that means. That red line is effectively the water quality limit or water quality objective for magnesium or EC. They're highly correlated. So when I talk about magnesium, it can effectively be EC and vice versa. Of around about 40 to 42 microsiemens per centimetre or 3 milligrams per litre. So you've got situations here where that's being exceeded, often, but not for long periods of time. And the question is, well, what are the implications of that? And at the time we were receiving these data, we had no real knowledge of pulse exposure effects of magnesium. Now, this is a system that's flowing through the wet season and you're getting those pulses, but the situation is equally relevant to a wastewater that is discharging into an ephemeral stream that is dry, and then the water comes and you're getting the discharges. So the work that was done to look into this was basically a large program of work that assessed toxicity of magnesium for relevant pulse exposures, and we worked at 4 hours, 8 hours and 24 hours, and those were based around the statistics, the descriptive statistics around the nature of those actual pulse exposures that were observed. And we also had our chronic continuous exposure data that had already been generated years earlier to derive that number, that red value. So this is just a pulse exposure toxicity plot for one of the species we looked at, which was Hydroviridissima, and basically, not surprisingly, as one might expect, as the exposure period gets longer, the toxicity gets higher, or vice versa. So here you've got a 4-hour pulse and an 8-hour pulse, 24-hour pulse, and then a continuous 96-hour pulse. And so basically we generated data like this for 6 local species, and those data were used to derive guideline values for each of those pulse durations. And then those data were effectively put together to create or construct a relationship between magnesium exposure duration and the guideline value. So you basically end up with the relationship that says, well, based on a given exposure duration, that guideline value should be around about X or Y. Now, the critical next step is at that stage, we're really just talking about guideline values, and that's step 4. But step 5 is the ability to turn those into water quality objectives that are actually used and implemented for the aquatic ecosystem. So in this situation, that magnesium exposure duration guideline value framework has actually been incorporated into the water quality objectives for Ranger uranium mine. So we're not dealing with a single number in a license here, which is often where where people head. Actually dealing with a decision tree that makes one take into account the pulse or exposure duration of any given pulse or pulses. And this is actually embedded in the regulatory framework. So it's an example, I suppose, of being able to offer a slightly more relevant and flexible approach within a license condition than just sticking a single number in that's not going to be relevant under certain situations. I'll leave it there and we'll go on to Shelley's case study.
Questions on that before we just move on? Yep, Chris. I'm coming.
Rick, can you just go back a slide? Actually, keep going, Shell. Oh, keep going, please. No, my question. I'm getting old. My question is lost.
See me at afternoon tea. Afternoon tea.
I have a comment too, Rick. I think the decision tree looks a little complicated, but we simplified it into a nice little spreadsheet. I think, and the operator really doesn't have a problem with it. I think that's a key thing to point out, and it actually is to their advantage because these short spikes were, causing a bit of tension with stakeholders and things like that. And to actually have something to go to and say, actually, it's not a problem. Like when they started happening, we said this, we don't think this is a problem, but we got the data to show it wasn't, and then we got the framework to actually and simplified it in a simple calculation tool to actually make it work. You got it?
I've remembered my question. What number are you what are you comparing to the guideline value, Rick? Instantaneous measures or time average measures?
That's a good question. And it's been over 5 years since I've been there, so I'd have to defer that one to Chris and Andrew because I honestly can't remember.
It's based on a duration. It's based on a certain amount of duration, and so your duration and magnitude goes into the calculator, and then you work it out. And one thing Rick didn't present was we went on and we actually had a look at, well, what if you get a short pulse and then a gap and another pulse and things like that? And we found a time weighted average was a pretty reliable way to do it. So there's some value in that because, 50 odd toxicity tests to go into that one curve on the right? People aren't necessarily going to do that, but I guess we put these up as examples because you might not want to go and do your 50 odd toxicity tests, but there's evidence in the literature saying, I mean, with caveats that maybe for certain contaminants, you might, think that a time weighted average might work. In fact, that was going to be a question I had, Rick. What was time weighted? Is there anything about time weighted averages for pulses within the guidelines?
I don't think so. I'll just talk loudly.
Yeah.
I'll answer it.
Yeah. Perhaps not. But other jurisdictions do use it, like USCPA use it, I think, time weighted averages and things. So yeah, it's something to consider if you've got those really short durations and things like that. But Shelley, thank you.
Okay, this is showing where I lost a slide this morning when I was pulling stuff together. I did actually have a cover slide on this, but it's gone into the ether. This is following on from a lot of work that ERIS has done, as well as a lot of other jurisdictions, just trying to just get away from that static single guideline value, particularly where you've got just a short-term pulse exposure, and also to where you've got a point source release coming into a system. So the example I'm using is where you've got flow events that may typically run somewhere from 18 to maybe 100 hours duration. But during that point, due to the rainfall intensity, whatever your system is, there may need to be a controlled discharge into the system. So rather than just waiting to see potentially what the effects of that might be, it's then going, okay, what do we think we can release and still have a level of confidence that we may be protective of that downstream receiving environment? So it's going from being responsive to more predictive, so that rather than just trying to measure the effects, let's put something in place that hopefully has got a level of conservatism to protect, but it's not overly conservative. A lot of this work has actually been pulled out of literature because, as Andrew and Rick alluded to, doing tox assessments is neither cheap or quick. So the example Rick used was just magnesium. When you're looking at a regulatory instrument like an environmental authority, you might have 10, 12 or 14 separate toxicants in that list. So you can imagine trying to set those short-term pulse exposure guidelines for all 14 elements may be really, really challenging. I'll also say that I'm presenting this. Chris did most of the hard yards on it. So if you've got really technical questions, call on him, please. So in terms of looking at the water quality envelope, it's sort of going from a 48-hour exposure, potentially trying to fit a curve down to 168-hour exposure and doing that curve fit. But again, from a regulatory instrument perspective, applying that in real time can be a little bit challenging. So the alternative is to offer something like this, where you have your parameter, you have your time less than 48 hours or your time greater than 48 hours. At less than 48 hours, typically what you're doing is applying your 80% species protection. So you're still using your default guideline values, but you're stepping back because of that short-term exposure. The risk of effect is considered to be lower than for a longer-term exposure at the same concentration. If you've got greater than 48 hours, we're defaulting back to the 95% species protection, because that's for a slightly to moderately disturbed system. Again, we're still using these default values for a system that's highly dynamic, but we're hoping that the conservatism in there, embedded in that, is actually still going to be protective of the system. The M values that come in here is the dilution factor. So that there's a minimum dilution factor that's applied to this, so that whatever you're doing, you're never actually going to go more than the value that's set there. So it's a minimum of 1, a maximum of 5. So you can't go down so that you're pumping twice as much water into your receiving environment. And also embedded that is that we're only taking 0.8 of the fraction of the receiving steam stream flow as well. But it does give an opportunity to just have slightly more flexibility in those really short-term release events that are happening when you've got a pulse flow within your receiving environment. One of the advantages of this is that telemetry wise, you need to make sure you've got real-time information on things like flow. Quite often you can have a real-time telemetry continuous data on something like conductivity, and if you're lucky, pH. But for most of your toxicants, you're never going to have that in real time because you're only ever going to have that as a result of the samples that you collect throughout that period. So by using conductivity as a proxy, you can also then do a little bit of validation checking that you're keeping within essentially what your framework should be. So that's all I've got to say.
Thank you, Shelley. Question?
Thanks. Not sure if I'm talking to you or Chris.
Either or.
Both. So is this published?
It sits within an environmental authority.
Right.
It is.
So it's publicly available.
It is publicly available, and I did actually get prior approval on this one, but it is anonymized as to which organisation it is. If you want more information, I can ask them. But yeah, this is where you're working at that interface between industry and the regulator and everything else. So it's, yeah, we'll do the work in this space and try and get that consensus between client and the regulator, but it's not really our place to be able to release this information, as much as I'd like to do it with a lot of this stuff.
Well, I mean, there would seem, if one develops a method that works, there would seem value in publishing such a thing so that it becomes much more widely accessible. So that's something that
I'm working on it. I'm working on it. I'm trying to wear them down.
Yeah, and now just also on the selection of the 80% species protection value for less than 48 hours. Andrew Boss and I were having a chat about that just before lunch, completely coincidentally. But if I have a bit of a concern if that's just an arbitrary selection.
Part of it was driven by going back to the literature, and wherever we had data available that provided us with responses at 48 hours, because a lot of the literature will actually give you, those responses, whether at 48, 72, 96, however long the duration, so you get those interim values. And I think there's also a couple of papers, correct me if I'm wrong on this, Chris, that actually also suggested that it's potentially a viable approach. But on top of that, we've also got that additional dilution factor embedded. So for the receiving environment, we've embedded another level of conservative in.
Okay. So, I mean, I don't know, I'm not sure because I'm still trying to get my head around the approach, but is another option to derive an acute / short-term guideline value to deal with the shorter exposures? And then you marry up that one with the longer term one in terms of the relationship between them.
I'll hand over to Chris on that one.
Wait, for the online.
Without wishing to contradict my boss too much, the 80%, as Rick suggests, is somewhat arbitrary because we've got, again, in dealing with the regulator, they keep pointing us back to the guidelines and saying, use the guidelines. So the 80% species protection was a value in the guidelines that was immediately accepted. So there was a bit of hunting around, trying to understand whether that worked or didn't work as a level of protection, but it was a number we could get. The regulator understood what the number meant in terms of or where it came from. The shape of the curve, the literature that was used was talked about a moment ago when you talked about your magnesium exposure. So I looked at your paper and took a curve shape and basically just it did a very simple curve fitting as to a proportional change at a 72 hour. We proposed to the regulator an envelope. We proposed to the regulator an envelope that went from 48 hours to 168 hours. They didn't accept that. The table on the right-hand side is what they came back with a sharp change at 48 hours. Now, I don't like sharp changes in regulatory context because you're either then trying to stay just above or just below, and there's a lot of fiddling when in actual fact it is a gradient of some sort. The other aspect, now that I've been identified as the architect of this, is the dilution factors, which were built on comparison of flow hydrographs and this is a rapidly changing environment, akin to your 4 to 8 hours, 12 hours pulses of flow. You've got a pulse of flow coming out of the storage. It's been routed through the storage, so it's no longer in phase with natural flows in the environment. We have everything from storm tracks through the environment and what that means for different flows in different systems. So the M factor was an attempt to try and be very conservative as the minimum sort of dilution that we would expect. But it's turned, with hindsight, it's actually a very complex arrangement to implement and totally dependent on your telemetry working and being available instantly through the process. So yeah, it was a means. We were trying to argue that pulse flows were not the same as ambient waters. And at the time, this was the best we could come up with. Apropos of my question earlier, we also take actual measures against the envelope, not a time average measure against the envelope. So there's an immediate, another great layer of conservativeness in that. But yeah, it's square pegs in round holes. It's trying to squeeze something into the available framework to go beyond the basic level that was available to us.
Thanks. It's great to see people working on these things, though, it really is, and try and move along. Let's move on to the next one. Oh, sorry, let me double check. I did miss a question earlier from Greg Clayton. He wanted to know if South Australia was the only jurisdiction using Titan. I thought so. Does anyone know if that's contrary? Anyway, we can ask around, but I thought that was probably the case.